Hi students, how are you? Now we will discuss ray optics spherical mirrors. In this, firstly I will discuss relation between radius of curvature and focal length. Later mirror formula. Then we will discuss ray diagrams also. Firstly, relation between radius of curvature and focal length. To understand the relation, imagine there is a concave mirror. We already discussed terms related to mirrors: pole, focus, center of curvature. Pole, focus, center of curvature always lie at equidistant manner. If you observe, from the pole to center of curvature, this become radius r. Radius r. Distance from pole unto the focus, focal length. We discussed actually these terms in previous video. Actually, relation between radius of curvature and focal length is r is equal to 2f. We are going to prove this. In simple manner, the distance between P and F and C is remains same, so that if P to F, focal length, distance from pole and to the focus, focal length F, and F to C also F. So R become 2 times F. That is the relation simply. But we are going to prove by using some geometry. Let us imagine AM is a incident ray, incident on the concave mirror. If a ray moving parallel to the principal axis, then what happen? According to ray rules, reflection takes place through focus. After reflection, it moves through the focus, rule number 1. Actually, light follows laws of reflection. Through center of curvature, we can observe imaginary normal. Dotted lines indicates that imaginary normal. Angle between incident ray and to the normal angle of incident I. Angle between normal and to the reflected ray, angle of reflection r. Let I is equal to r is equal to theta. Angle of incident, angle of reflection remains same. I will move with theta. This is theta. This is also has to be theta. Interior opposite angles we can observe here. This theta. This is theta. This has to be theta. Here, if you observe the triangle MCF, from the triangle MCF, this theta remains same thetas. So these opposite sides also has to be same. Why? Because once recall isosceles theorem from mathematics. If you observe isosceles theorem statement, there is a triangle theta 1, theta 2, theta 3. Three angles. If two sides in a triangle are equal, side A, B and C. Two sides in a triangle are equal, then angles opposite them are also equal and vice versa. Suppose for side A and B are equal, A is equal to B. If you observe, for side A opposite angle is theta 1, for side B opposite angle is theta 2. So we can write like this. Why? Because two sides equal. Whenever in a triangle two sides are equal, then angles opposite them are also has to be equal and vice versa. Here this theta and this theta remain same. From this triangle we can observe, since thetas are equal, why don't we equate sides also? That is why for this theta opposite side is CF, and for this theta opposite side is MF. Remember equation number 1. CF is equal to MF. And now, according to paraxial approximation, M is coincide with P. Why? Because in case of paraxial approximation, angles are negligible, so that we can observe M is coincide with P. So instead of P, we can put M also. So can I write M is equal to P? Why? Because M is coincide with P. Now from 1 we can write CF is equal to PF. Why? Because M is P, coincide with P. CF is equal to, where M is P, F, PF. If you observe this relation, what about CF? CF, we already discussed. Distance from pole unto the focus unto the center of curvature remains equal. C to P, R, radius of curvature. Since these two distances are equal, we can write CF is nothing but R by 2. R by 2. So CF is R by 2. What about PF? PF is focal length F. This is the relation between radius of curvature and focal length. It can also be written as R is equal to 2 times F, or you can write small f, you have to write. You can write 2 by R is equal to 1 by F. These are the different forms between R and F. Now we will discuss mirror formula. Before moving to mirror formula, you should know sign convention. Why? Because we will use these sign conventions. Sign convention in case of mirror or for lenses also, we will use the same sign convention. Sign conventions are very important. In case of mirrors and lenses, sign convention remains same. Suppose I will take concave mirror, pole, focus, center of curvature. Imagine any object is here. There is a object, candle. From the object, rays are moving this way. So these are the direction of rays propagation. Firstly, you should observe that all distances are measured from the pole. All distances are measured from the pole. Let us imagine vertical imaginary axis as Cartesian coordinate system. Suppose this is plus y, minus y. And the principal axis as imaginary x-axis, plus x, minus x. Now, firstly, you have to remember all distances along principal axis are strictly measured from the pole. Distances measured from the pole or optical center, optic center. Now, second one, in the direction of ray propagation, you have to take positive. Rays are moving this way. After vertical axis, you have to consider this side, all positive. In the direction of ray propagation, take positive. This means this side, all positive. Next one, after reflection, what happened? Reflection takes place this direction, opposite to the direction of propagation. Reflected rays are moving. So rule is opposite to the direction of ray propagation, opposite to the direction of ray propagation, take negative. Means imaginary y-axis, left side, all taken as negative. Sign convention is negative. Next rule, above the principal axis, above the principal axis, here you have to consider heights. Take positive. Above the principal axis, take positive. Above, this is height of the object, you have to consider sign convention positive sign. Height is positive. Suppose object is image is, I got here image, so height is positive. Height of image also positive, you have to consider like this. Next rule, Below the principal axis, again heights only take negative. Suppose I got image like this, so inverted manner, you need to consider this distance, this height as negative, height of the image here negative. So below the principal axis heights are negative. Suppose I got the inverted image like this. In case of lenses, we will observe this kind of nature. Here height is considered to be negative height. So above the principal axis positive, below the principal axis negative. On the basis of these conventions, sign conventions, we will see how object distance, image distance will be observed. I will draw one diagram. Concave mirror, object is there. I will draw in case of concave mirror and convex mirror also, don't worry. Pole, focus, center of curvature. Ray travels through focus, it will move. Through focus, parallel to principal axis, it will move. Through focus, ray move, parallel to principal axis, it will move. Suppose I got image, this is object, this is image. Object distance always treated as u, denote by letter u. Image I got here, image distance always denote by letter v. V is the image distance. We know pole unto the focus, principal focus, distance is focal length, and pole unto the center of curvature, distance taken as radius of curvature, or if you apply sign convention here, and image distance also taken as negative. Why? Because left side, right side all positive, left side all negative. Image distance taken as negative. If you observe focal length, small f also taken as negative. Why? Because left side only. Opposite to the direction of ray propagation, distances are measured. Opposite to the direction of ray propagation, distances are measured. So negative. Radius of curvature are also negative. These are all negative. I will draw sign convention for a convex mirror. Now you will get some confidence. Suppose if I draw a convex mirror, pole, focus, center of curvature. Object is here. All distances are measured from the pole. Object distance u. F, small f, focal length. This is focal length, small f. And here to here, radius of curvature C2, pole, radius of curvature R, focal length F. For example, I got image here as virtual image. I got image here. So this has to be image distance. V is the image distance from this point to pole, image distance. Now apply sign convention for the convex mirror. If you observe object left side in the direction of ray propagation all positive, this imaginary y-axis remaining right side all positive, left side negative, u taken as negative. If you observe image distance, image formed opposite to the object, right side formed, so v taken as positive. If you observe f, focal length taken as positive, radius of curvature r, right side, r also taken as positive. These are the sign conventions. Now we will discuss the derivation of mirror formula. Again consider concave mirror, pole, focus, center of curvature. Suppose any object, point object is kept here. Imagine any ray incident on the mirror as OM is